You okay with this being recorded, Giovanni? Just checking. Okay.
Yeah.
We welcome Giovanni, who's now working at Quantinuum. We're going to be talking about quantum linear optics via string diagrams. So take it away.
Okay, thanks. Can you see the full screen? Yeah?
Yeah.
Okay. So I'm going to talk about a recent paper with Bob, where we went through some of quantum linear optics with string diagrams. And so my plan for the talk is I want to start by giving some intuition of the kind of photonic hardware that's available, and that's basing most of the proposals for building a photonic quantum computer. And I'm going to talk about how to formalize these basic optical components. And first, I'm going to give the classical interpretation of linear optics, and then I'm going to talk about how to quantize it using Fock space, and finally, I'll go through like how to apply this to get universal quantum computing, although it's probabilistic, and I'm going to explain some of this at the end. So if you want to build a photonic quantum computer, and there's different approaches. You can use also other degrees of freedom of the photon, but in general, what you need is single photon sources. And so there's two main methods for generating single photons, and the most popular one is spontaneous parametric down conversion, where you basically throw a laser on a crystal, and it emits a pair of photons that are entangled, and you can kind of check from one of the photons if the other has been generated correctly. And also you can use this idler photon to align different sources, sources of photons, and then that's how you kind of build up your setup. So this is quite expensive in practice. It's a probabilistic process, and it doesn't scale that well. So recently there's been proposals for using quantum dots, which are like basically, from what I understand, they're like atoms, which if you throw a pulse at them, you excite them, and then when they decay, they emit a photon. So you can kind of use these atoms to generate streams of photons, and yeah, that's useful in practice. So these photons, once you've generated them, you can put them inside a photonic chip, or it could be also a bulk optics setup. It could be on an optical table in a physics lab, and yeah, they go through these interferometers, and they enter from some positions, and they come out from some other positions. At the end, in order to see where they came out, you need photon detectors, which they basically work by putting a metal plate where like there's a current going through, and then when the photon hits, it changes the current, and this has to be put inside a big fridge that has to be at like around 0 Kelvin. Otherwise, any other photon could hit the plate and fuck up your experiment. So so these are three ingredients: just photon sources, photonic chips, and detectors. And in 2001, Neil Laflamme and Milburn showed that these ingredients are enough to perform probabilistic universal quantum computing. So how is this possible? I mean, it's very simple. The types of ingredients that you use are these linear optical ingredients, which are very basic ingredients. They're so we can formalize this setting by defining a category LO of linear optical circuits, which is generated by two basic physical gates, the beam splitter and the phase shift. And then these have an interpretation in matrices with byproduct. I mean, you can interpret the beam splitter as this 2x2 matrix. So here, like each wire gets sent to dimension 1. So a component that goes from 2 wires to 2 wires is going to be a 2x2 matrix, and the phase shift, which goes from 1 to 1, is going to be a 1x1 matrix. you can compose these components in sequence to form, for instance, a Mach-Zehnder interferometer. This is the diagram for a Mach-Zehnder interferometer. And again, and you get the semantics, the classical semantics in matrices with byproduct by multiplying the matrices. If you put two matrices in parallel, then you take the byproduct, so which is the block diagonal matrix built like this. And you can build like more complicated setups. Usually you start from MZIs. Each of these white boxes here would be an MZI. And then you can put them in arrays. And it turns out that by just using these basic components, you can parameterize any unitary map on M modes. So for any, and by M unitary U, there is some circuit of MZIs with some values of the parameters, such that the classical interpretation of the circuit is the unitary. So this was shown by Reck et al. In 1994, and then there's been improvements. There's a paper by Clemens et al. Where this architecture is shown to be universal. So the first step that we're gonna take is we're gonna take these basic components and open them up into some slightly simpler components. These are the copy and merge. I mean, let's not call it copy, split and merge. And when I draw a number like this on top of a wire, I mean a phase or an endomorphism on one wire. And here, basically, we're opening up the matrix. This is going to become clear if we look at this calculus of paths. So it's generated by a comonoid, a monoid, the swap, and some endomorphisms. And the elements of these endomorphisms, so these R's, they're from some set, which we're going to take to be a semi-ring. So we can interpret these basic diagrams again in matrices with byproduct. So we can give it a classical interpretation, and we get, which is pretty simple to do. And you can check, you can check that the axioms of these of the path calculus hold in the semantics. So what are these axioms? So the main axiom is the bialgebra law. This monoid and comonoid form a bialgebra. Then this is like just their monoids, comonoids, etc. And then you have homomorphisms. So every phase like this can be copied through the comonoid, and then you have that these homomorphisms form a semi-ring. So they have an additive structure and a multiplicative one. So one can show that these axioms are complete for the category of matrices with byproduct. So in fact, there's an equivalence between the path calculus and this category Math plus. And it was first shown by Bonke, I think. I mean, I'm actually not 100% sure that this was the first time it was shown, because it's a very trivial statement, but it was definitely used by Bonke, Sobocinski, and Zanazzi in 2014 to model signal flow graphs. So yeah, this is the classical story. We have like calculus. We analyze this story inside these optical circuits. Those to the category product, and so it's the hello.
Hello, we lost you for a minute there.
Was it me or was it, okay, so it was me.
I think it was you, yeah.
Okay, then I moved to, I don't know, closer to the, sorry about that. So I was talking about, okay, so we want to quantize this semantics. I don't know where you missed. So I guess what we talked about so far was that we have linear optical circuits and we can decompose them using the path calculus, which is a simple calculus generated by algebra with endomorphisms forming a semi-ring. We want to quantize these calculi. So we want to quantize the semantics, and we're going to do it by using the bosonic Fock space functor. This is a functor that goes from mat plus to vector spaces with tensor product or Hilbert spaces. And it's defined on some object, so vector space H of finite dimension, as the direct sum over all i's of the tensor product of H, the symmetrized tensor product. So this is the tensor product quotient by the equivalence relation where 2x tensor y is equivalent to y tensor x. So if we look at the nth component in this direct sum, putting I equals n, calling it Bn of H, we get like that it's just the symmetric tensor product of H n times. And it's isomorphic to the free vector space over phi mn, where phi mn is basically the set of occupation numbers of n photons in m modes, where m is the dimension of H. So yeah, here is just a list of natural numbers of size m, which sum to n, the number of photons. Okay, so we can extend this. So here we've defined the bosonic Fock space on objects. We can define it also on arrows, and basically by defining the nth component to be the symmetrized tensor of the matrix with itself n times. And to define this, you can use a natural transformation alpha, which relates the symmetrized tensor product with the free tensor product, the normal one that we use all the time. And yeah, it's defined in this formula as a sum basically over all the possible orderings of a set of indistinguishable photons. So you have indistinguishable photons in your bosonic Fock space. You can embed them into the free Fock space by summing over all the possible orderings of these n photons. And then you go back with the dagger, and you get the image of A on the nth component of the direct sum. And you can do this for all n. So you can show also that this satisfies that the direct sum is sent to the tensor product. Here it's symmetrized, although it embeds in the tensor product. And so this was first shown by Jamie Vicary in 2008. And it was also used before in the 1990s by Blut, Panangaden, and I think Seeley, as a model of the exponential modality in linear logic. So in fact, this relationship between the biproduct and the tensor product is one of the defining axioms of the exponential modality in linear logic. So we have this definition of kind of the quantum semantics of these of a matrix, which is given by taking the bosonic Fock space of it. And what we can show is that this model is in fact equivalent to a more concrete model, which was introduced by Aronson and Arkhipov. And I will talk about it a bit more later on, but basically the amplitudes are shown to be the same as computing the permanent of a matrix that's obtained from, depending on the input and output states, from the basic unitary U. So So yeah, this is quite actually the proof of this is actually using like known techniques that simply symmetrizing the tensor product, and but it kind of shows that there is this computational alternative, I mean, way of looking at this model of linear optics, and it shows also that what we're computing is hard because this computing permanence of matrices is a hard problem classically. So let me just say a bit more about this. So what we're computing, right, the amplitude, we never actually ever observed the actual amplitude. We only observe the absolute value squared of it, and we get an additive approximation of this absolute value squared. But Aronson and Arkhipov showed that if a classical computer can find an additive approximation of this value, then the polynomial hierarchy collapses. Okay, so we have this semantics and we've kind of characterized it, but what we want is to reason about events with multiple photons, and we are gonna do it by building a graphical language where we can represent different optical protocols. So this is just basically we're gonna use the path calculus together with creation and annihilation of n particles in a mode. So we just add these two generators to the calculus, and now we can interpret QPath directly in Hilbert spaces with tensor product. Basically by composing, first you go from, so for all the generators of path, you go into mapped matrices with biproduct, and then you go into the tensor product. And these have a direct interpretation in Hilbert with tensor products. So the basic generating object, so the wire of these diagrams, is mapped to the vector space L2 of n. So it's the free vector, it's kind of free, the canonical vector space with basis elements being the natural numbers. So these are really just the basis of the space on one mode, and phases are gonna get mapped to in this way. And then the split is mapped to basically is like you have n photons coming in, and then there's all the superpositions of k photons on one side and n minus k on the other, with coefficients given by n choose k square root. And then you can interpret also all the other generators basically by taking this, if you take the adjoint of this, you get the monoid, and then the rest is all, and then you've defined all the generators. The swap is the swap, and then you've defined all the generators. The unit is 0. So the white node is the node with n equals 0.
Okay. What is delta on the previous slide? B of delta?
Yes, so delta is the comonoid. So if I go back to the generators of path, this one is what I'm calling delta. And so I'm just computing the composition of this functor into matrices with biproduct, and then embedding it into the Fock space, and what you get is actually this.
Thank you.
Okay, so if we add some axioms, so having added these creation and annihilations, we're gonna have more equations that and ways to reason about these diagrams. So we definitely have all the path axioms are true in this new interpretation, because the semantics is just defined by functor composition. So if something is true in the first, it has to be true in the second. The only things that are new in this calculus are the creations and annihilations, so the black nodes, and we can axiomatize them like this. These are the axioms that we found hold, and they're definitely not all, they're probably not all of the axioms that you need, but they're enough to show some results. So we have this scalar law, just says that you can that you can pull out a phase when two photons match. This says that a photon cannot, like, you cannot post-select 0 photons on 1 photon. And then you have this normalization law, which tells you how to go from these states with n particles to single particle states put together into some merged together into a mode. And then we have the branching law, which is really the thing that you have extra in this case, and which, if you want to formalize it, requires to enrich your category over sums. And it just says that a photon if you put a photon in a split, then it goes either left or right. I mean, either on top or at the bottom. Okay, so we can use these basic axioms to derive some known rules of linear optics. One is that the commuting relations of creation and annihilation operators. If you create a mode and then you destroy a mode you create a photon and you destroy the photon in the same mode, that is equivalent to, if you use the bialgebra law here, you get this diagram. And then if you use the branching law, you get these two terms. And this one, if the photon goes up, then it matches with this photon. But if the photon goes down, then there's no photons here. And by the Born law, that doesn't hold. So this has to be white coming here and gives you the identity. And this one similarly gives you the other part of the commutation. So another thing we can show with the calculus is the Hong-Gao-Mandel effect. So this effect is basically saying that if you throw 2 photons on a beam splitter, the probability that and if you throw them exactly at the same time, they have to be coherent within the coherence time. The 2 photons, they never come out each their own way. They always bunch together. And so you can check this by computing the probability that if you put 2 photons inside the beam splitter, so this is just the representation of the beam splitter, removing the 1/2, which we don't care about. And so if you use the branching law, you can prove that this is equal to this sum of 2 terms. And the 2 terms correspond to, in the first case, the photons are both reflected. And in the second case, they're both transmitted. And since these have amplitude I each, you multiply these entries and you get -1, and here you get 1. So the 2 possibilities of them both reflecting and both transmitting, they cancel out and they give you 0 probability for this event. So I've left it a bit until here to show the way that Aronson and Arkhipov defined the model of linear optics, just because it becomes simple then to see how the Q-path calculus is really just mimicking the same process as is described by Aronson and Arkhipov. So what you do, right, to compute the probability of output state J and input state I for a chip C, you take the classical interpretation of C in matrices with biproduct, so a small matrix, and then you modify this matrix with respect to I and J, and this is explained here. And you say that you first construct the matrix Uj by taking J copies of the jth column of U, and then so you basically have these occupation numbers, and you pick columns and rows according to the number of photons in each of the input and output modes of the circuit. And this is mimicked at the level of Q-path. If you have like an input state, this would be input state 1, 0, 2, and output state 2, 0, 1 on a chip with some coefficients. Then you could just compute the underlying matrix and kind of reduce this all the way to a bipartite graph where you've split every time there's 2 photons in the same mode, you pick twice that entry. So here you have you've computed this matrix, and this matrix, so the modification of U of C with respect to I and J is always going to be an n by n matrix, where n is the number of photons. So at the end, we can always take any QPath diagram that is closed, so that has input and output specified, and turn it into a weighted bipartite graph, which corresponds to basically this matrix Uij. So you can use this to show that for any closed diagram, the rewrite rules of QPath are complete for the bosonic interpretation. So basically what happens is, first you reduce your diagram into this weighted bipartite graph. And once you have the bipartite graph, you use the branching law to split it up into all its components. And you can see pretty easily that this corresponds to matching input photons with output photons through paths on the matrix or on the weighted bipartite graph. And so, so this corresponds so the amplitude of this diagram corresponds to computing the sum of weights of the perfect matchings of this bipartite graph. Okay.
Giovanni.
Yeah.
Are you saying that you're splitting the diagram up into a sum of diagrams?
Yeah.
Okay, so this calculus is not a calculus of diagrams, it's of sums of diagrams.
Yeah. It's a calculus with sums. Yeah, sum enriched monodal category, free monodal category.
Okay, but and then completeness means you can also take sums of diagrams back into a single diagram if you do the rewrite rule in reverse. Because essentially using this completeness means you split your diagram up into all these different components.
Sorry, I'm not hearing. I'm having problems with. I'm sorry.
Yeah. So you are essentially just cutting all the wires, and then you get this an exponential set of disconnected diagrams.
Yeah, exactly.
Okay.
So in the end, it's really like the calculus itself is just mimicking what happens in this definition. So you're computing the permanent of a. So you first take the matrix, your diagram, you rewrite it so that you get at the end this weighted bipartite graph, which corresponds to the matrix Uij, and then you compute the permanent. And computing the permanent is equivalent to computing the sum of weights of perfect matchings of the graph. So yeah, here there's no like advantage in using this approach, except for the fact that now you have a calculus for representing your diagrams, for representing events with multiple photons. And also, this is important, this theorem is only true for closed diagrams. And it would be really interesting to look at equivalence of these protocols outside of this 0-0 sector, because if you, we will see now diagrams with some open wires, that there can be many equivalent representations of the same processes using different number of photons, for instance. So how do we apply this to linear optical quantum computing? So the idea is simple. So you want to replicate qubit computing in the Fock space. And the way you're going to do it is you're going to encode a qubit as a pair of spatial modes, as a pair of optical modes with one photon in them. And if it's on the right, it's H. So the basis state 0 if you want. And if it's on the left, it's B, the basis state 1 of the qubit. So our qubit has basis HB for horizontal and vertical. Yeah, so we have this that tells us how we're going to encode it. Now we want to map all qubit operations onto the Fock space. We're going to map the basic generators of the ZX calculus. which I think everyone here is familiar with. And yeah, we're gonna take this simple way of generating the ZX from some basic operations. So how do we map states? So this would be the H and V, right? In the sense that they're the basis states 0 and 1 in ZX. And so we can map them as I described before. Similarly, you can map effects by simply flipping these diagrams, and you can map the Z effect by taking this. So it's H plus V. If you think about it, H plus V is all the possibilities in which there is at most one photon in the thing with phase plus. So this is the diagram, the qubit diagram that corresponds to it. Then we can map single qubit unitaries. So the Z phase alpha gets mapped to a pair of, so one wire gets mapped to a pair of wires, and alpha gets mapped to e to the I alpha on the second one, so on B. Then we can map the Hadamard matrix. Is sometimes people like to use that. There's different conventions for what the right beam splitter is, and sometimes people use the Hadamard matrix as the definition of beam splitter, so it's this linear map. And sometimes they use the ones that I've defined before, which is what I call the standard beam splitter, and has the coefficients i's here. Here I'm taking everything up to scalars. Here I'm saying the blue wires correspond to a wire with a phase -1, and the red wires correspond to a wire with a phase I. So using these two beam splitters that we've defined, we get two versions of the Hong-Gao-Mandel effect, which can be kind of seen graphically in a simple way. So, right, this was the same one that we checked before, the Hong-Gao-Mandel effect, where we had I, and we split this into the two perfect matchings, which are straight and across, and these two cancel out. And similarly, for this other beam splitter, they also cancel out. They're basically the two beam splitters correspond to two Fourier transforms. Here it goes from the x to the from the z to the x basis, and here from the z to the y basis. So a very useful ingredient when you do linear optical quantum computing are fusion measurements. These are ways of basically measuring the Bell basis in dual rail encoding, and you can represent them in QPath in a very simple diagram where you have like 4 modes coming in, 2 coming out, and here you're saying there is at most one photon in the 2 middle modes. So if you look at all the possible initial basis states with 2 photons, this condition that there's one photon, exactly one in these 2 middle modes, is only satisfied by 0, 0, this state and by this state. Here and here they get selected away, and so you get in the end this linear map. Then you can also define a Bell state in dual rail encoding, and this is kind of engineered, but actually a kind of you can both think about it from QPath, but I'm taking it from one of the first protocols for generating Bell states, and so this would be the diagram of the Bell state. If you look at it, there's kind of 2 beam splitters inside, and so 4 photons get created, 2 photons are annihilated, and these kind of 2 beam splitters that much like this. So if you use you can reason about this diagram by basically saying, okay, what's the probability that I get two photons here? That I put the two. If I put the two photons here, then they cannot be. These two have to go here, so they don't go here, and so you're left with this part of the diagram, and you get this shape. And similarly, you can do it with all the choices of where you put the photons, and you get different different smaller diagrams. And each of these is a bit like these versions of von Braun-Mantel. Some of them they become 0, and some of them they amplify. So here, in this case, it's 0. In this case, it's 1 because it's yeah. I guess the symmetric ones they cancel, and the asymmetric ones they amplify. So this one cancels, and this one cancels, and this one cancels, and you're left only with HH and BB. I mean, that's basically all you need, because if you have fusion measurements and you have Bell states, then you can use them in conjunction to build, for instance, the Z spider that splits. And then you can keep bending wires from Z spiders to generate bigger Z diagrams. And you've mapped all of ZX, so you can map all of qubit linear maps onto the photonics. But notice that in all these protocols that I've shown, we're post-selecting in a lot of places. And every time, like, the probability of this happening gets smaller. So if you just take any ZX diagram and you interpret it using this functor into optical protocols, you will get exponentially lower probability of the actual circuit being executed in the right way. So the actual ZX diagram being executed, because most of the times these photons are not going to be found in those spots. And that's kind of what I'm still trying to understand a bit better, and still is open work, I think, is to understand how to increase the probability of success of these protocols. Because the main reason for this protocol for linear optical quantum computing to work is that basically Neil, Laflamme, and Milborn showed that the probability of success of a protocol may be increased to arbitrarily close to 1 by using additional ancillary photons. So if you want to do a protocol like this, and you can make the probability of success higher by increasing the number of photons. And that's the kinds of equalities in QPath that we still don't understand well. Yeah, so I guess this was one of the first future direction. Like, this is only one functor from ZX to optics. Are there other better ones, and how can we kind of parameterize them and look at the best? How do we measure the probability of success of a protocol? Is there a fast way of looking just at the diagram and understanding the probability of success, or do we have to compute all the amplitudes? Another question, I think, on the theory side, this kind of, it would be interesting to link it with the work also of Supoczynski, Boki, Zanazzi on feedback and signal flow, data flow programming, because this is data flow programming and feedback is used a lot in linear optics, and it allows for and it also allows for universal quantum computing in different settings. Another direction of future work that we're currently working on with Alexis Toomey and with Richie Young is to implement these functors in DiscoPy, that in order to compile qubit circuits or MBQC patterns or anything you can represent with ZX onto photonics. And then I hope that we will make some experiments and on real devices as well. So thanks. This is all.